Good morning, students. Welcome to another Video Code Lab tutorial in machine learning. Today we are looking at Module 9 content, so deep learning, specifically convolutional neural networks. These are well suited for image classification tasks with their multiple layers, their pooling layers, flattening layers, and dense layers. And so we're going to be using TensorFlow. So TensorFlow is a popular machine learning library for building and training models. And we're actually going to use as part of that Keras. So Keras is a high-level API. So anything high-level tends to implement or make things easier for us. API for building neural networks using TensorFlow. So we're going to use those two to build out the CNN today. We're also going to be using matplotlib for visualization as far as validation and the loss function. We're mapping that out because we want a very intuitive example so we can best understand it. Okay, we'll be testing or training our model on what's called the MNIST dataset, so Modified National Institute of Standards and Technology. This is a common dataset used in training image processing systems, or commonly used in the field of machine learning. I have a web link that you can visit. So the database contains 60,000 training and 10,000 testing images of handwritten digits. Essentially, we are recognizing these digits, or teaching a computer to recognize these digits. Okay, and you can read more about it here. Our training and testing split will be exactly that: 60,000 training and 10,000 testing images. Okay, so let's get started. We're going to be doing this in VS Code. So what I'm going to do is create a new file called Convolutional, or let's just go cnn.py and create a new file. It'll all just be in one file. And we're going to need a few imports. So first things first is we want to activate our environment. So let's go ahead and do that. With this command, and we're not going to be using Anaconda, so you could do that in Anaconda as well, but for this purposes of this, we're going to activate with Python. Okay, so we can tell here visually that our environment is activated. Again, we create environments just to encapsulate all of our dependencies so there's no conflicts between projects. Okay, the next thing we're going to do is run pip install TensorFlow and matplotlib. So we should already have matplotlib, but for good measure, we're going to make sure that is in there too. And we're going to install both here. So this will take a little bit. TensorFlow is quite large, as you can see here with the file sizes. So just be patient. Okay, so again, to restate, we are effectively building, training, and evaluating a convolutional neural network to recognize handwritten digits using the MNIST dataset. Okay, so let's get started while that's installing with some import statements. So we're going to import TensorFlow as TF. Again, this is our a popular library used in machine learning for training and building models. Then from TensorFlow, we're going to be accessing the Keras module, and we're going to import layers and models. Okay, this will aid us in building out our layers for our network. Okay, so we have that. Next, we're going to write from TensorFlow Keras. We're going to import our MNIST dataset, and this is a very common dataset that's used for machine learning tasks. So we have that. And next, we're going to access the utils module. We're going to import what's called categorical. Okay, and we can make a note here. This is a utility to convert integer labels to categorical or one-hot encoded format. Okay, so we know what one-hot encoded format is. We're essentially converting to binary our labels. All right, and then finally, we can import matplotlib and pyplot as PLT, the alias PLT, and we've done this numerous times before, and we're going to save that. Excuse me. Excuse me. Okay, so that comprises all of our import statements here. And what we want to do is just run the code and see if we get any issues. Okay, so it looks like it's good. So I'm just going to cancel that out and save it. If you see any red or any issues there, then we might want to explore any installation issues, but so far it looks good. Okay, so the first part of this is we're going to load, and we'll make comments along the way, the MNIST data set, our database. Okay. And we're going to start with this. So train images, train labels. So training images and labels, and then test images, test labels. And you can see this is for our splitting. This is returned from the MNIST, a method called load data. Okay, and we can save that. So essentially, it has, using these imports, we've made the loading of data quite simple, and it's already split. So we can make an additional note that our training images comprise of 60,000 images, whereas testing is 10,000. Okay, so that is the split already, and if students are accustomed to splitting data or generating synthetic data using random. But here, once it's nice and easy to load and also to split the data, and it's already ready to go. Okay, so that is easy. Okay, so the next part here, and this is a little tricky, is we're going to pre-process the images. And how we're going to do that is, or the reason why we're going to do that, rather, is because TensorFlow expects a certain type of image. So each image is 28 by 28 pixels in dimensions. But TensorFlow expects, or this model is going to expect, grayscale images. Okay. So that's the reason for this conversion. Excuse me one sec. Okay, so essentially what we're going to do here next is we're going to reshape the images to add a channel, an additional channel dimension, so a color channel, and it's going to be used for grayscale. And we're also going to do what's called normalize the pixel values. This is all pre-processing in order to prepare the data for the model. Okay, so let's perhaps write some more comments here. So we're going to reshape the images to add a channel dimension. So 1 for grayscale. And we're also going to normalize the pixel values to a specific range. 0 and 1. Okay. All right, so what this means is that each pixel rather has a single intensity value as opposed to 3 for, say, let's say RGB. Okay. So this simplifies the data set. So what does this look like? Well, we're going to create a variable called train images, and this is equal to train images reshape. So we're going to access the reshape model, and this is where things get interesting. So our training data consists of 60,000 images of 28 by 28 dimension, and we're going to put in this additional channel here, so 1 for grayscale. And we're actually going to convert the type to a float, so a decimal number. Okay, and this normalizes the pixel range. Okay, so 255, there we are. So there is a lot going on, but you can see we're pre-processing the images to grayscale. We're normalizing the pixel range and preparing these images to be fed into the neural network. Okay. And we're going to do the same for the testing images. So we can essentially just copy that and change this to test images, and then this to test images reshape. But our training set is only 10,000. Okay, same dimensions, same one channel for grayscale, same float 255. Okay, so make sure you've made the changes there and save. Perfect. So we're going to make a note here. Normalization helps improve the model performance by scaling pixel values to a range between 0 and 1. Okay, so we can save that here. So a lot going on here, but we can pick apart as best we can and make sense of these numbers. We know, a common method is converting integers to floats and things like that, and we're normalizing the pixel range to improve the model performance. Okay. All right, and then we added a channel dimension for grayscale. So very interesting stuff. Okay, but so far this should make sense. Let's keep going. Okay, the next part of this is, if you look at the training and test split, we also have these labels from the MNIST dataset. So these labels we're actually going to convert to one hot encoded format, so zeros and ones. Otherwise, they would just be integer labels from 0 to 9. So what does this look like? We'll go train labels equals two categorical, and we imported that up above, and we're going to pass in the train labels. And we'll make a note, transform training labels to one hot format, and we're going to do the same thing with the test labels. Okay. Whoops. I just gotta make sure I'm still recording. Good. So test labels to categorical, and we're gonna put in the test labels. Okay. And essentially we're doing the same thing. So to give you kind of an idea of what this is doing, we'll make a note. So this converts integer labels 0 to 9, so our number system, to one hot encoded format. And we know what students know at this point what one hot encoded format looks like. For example, 3 becomes 0, 0, 0, 1, and 1, 2, 3, whoops. Okay, so that should be 10. So we should have 10. So you can see 3 should be converted. Okay, and these are just placeholders. Okay, if it's 0 based indexing. Okay, so this would be 3. Okay, so we're converting to one hot encoded format, and this is how we can do that with this 2 categorical method that we imported up here. So far we've imported the data, we've split the data, we've reshaped the data, we've normalized the pixel range for model performance, and we've one hot encoded the labels to this format here. Okay, so let's keep going. Okay, the next part here is actually quite interesting. And I do want to note that I have included the CNN lecture PowerPoint and the activation function lecture PowerPoint, as well as the MNIST dataset link for students, just to ensure that they can have a look at these if they need a reference, because there's a lot of information in here that we went over in class, but you can peruse these materials to dissect the code even further. Okay, the next part here, and this is quite intriguing, is we're creating a data augmentation, what's called a data augmentation generator. Okay. So what this is doing essentially is we want to prevent overfitting. So if, let's say, our model is introduced with images that don't necessarily fit exactly what the model's been trained on, it will still have the ability to generalize on unseen data. So pictures that perhaps are slight variances, and that could include rotated images, width and height changes, zoom changes, shear changes. So basically, different aspects of what a picture could look like if you were to manipulate it in 2 dimensions. Okay, so scaling, shrinking, rotating, shearing, zooming, that sort of thing. Okay, so what does this look like? Let's create a variable called data_gen. And this is accessed through TensorFlow and Keras, and what's called pre-processing. I gotta get this right. It's a lot of dot notation here, but eventually we get to this image data generator. Okay, and this takes a lot of arguments. Okay, and we'll go through each one. So we're going to account for rotation range. So you can envision a image that's being rotated. So we're going to randomly rotate images by up to 10 degrees. So keep in mind, this is what we're training our model on. So these variances in rotation, we're also going to account for width changes. So width shift range we can account for. Randomly shift images horizontally by 10% of their width. We're also going to do this for height. also 10% in decimal format. And rather than, I'm just going to change vertically, height, and also zoom. So zoom range, also going to be 10%. And there's a lot of spots where you can get this wrong or make mistakes. So just make sure you're just watching the syntax and saving as much as you can. So we're going to count for 10% shift in zooming. And then our last one is going to be shear. So we're going to count for a shear range of 0.1. So randomly shear the images, or distort them, in other words. Okay, and no comma after that one. Okay, so you can see this method, even though it's a kind of a mouthful as far as the dot notation to access, this gives us the ability to account for any sort of real life adjustments to images. So let's say if we're uploading an image and the user has sheared it or zoomed in or made it a different shape, it's still going to count for that. Okay, perfect. So let's save that. All right, and we're going to keep going. Next, we're going to define this convolutional neural network model. Okay, we are going to use what's called a sequential model, which allows us to stack layers on top of each other sequentially. So this is when I would refer students to the PowerPoint lecture. Actually, let's get that open. Let's get that open here. And just look at a visual of a convolutional neural network, and you can see in these pooling layers, they're stacked up on top of each other. Okay, this is these layers where they're grabbing kernels or filters or segments of these images. And this is going to allow us to do that. Okay, so have a look at this. So kernels, they go to the pooling layers. Those get sent to a flattening layer, which prepare them for these fully connected layers. And then finally the output. Okay, so feature extraction, classification in the fully connected, and then we have a probabilistic distribution. And again, I go back to that idea that machine learning is fundamentally based on probability, okay, which is pretty neat. Okay, so have that handy because we want to understand how this stuff is working. Okay, so we're going to define a model as model sequential. Okay, and just be sure to get the spelling right, otherwise that's not going to work, and save it. And then now we're going to begin building our model. So let's add layers to the model. And let's make as many notes as we can. So first, convolutional layer will extract features from the images using 32 filters or kernels of size 3 by 3. And that's a common size, or 5 by 5 is a common size as well. Okay, so let's go ahead and save that. All right, now we're going to begin with the code. So we have this model add, and the first argument is going to be layers. We're going to add a convolutional 2D layer, and that corresponds, if you look back here, these are 2D layers, so two-dimensional layers. And then this method, this D should be capitalized. Let's be careful here. And there's going to be a lot going on. So the first argument is 32 filters, of which 3 by 3 kernels, 3 by 3 size, and that should be a comma. The next argument is going to be the activation function. Okay, and this is going to be relu. And this is why I included the activation function lecture. And let me open that. Okay, because we need to understand how ReLU works. So ReLU, rectified linear unit, it's a popular activation function. Again, it's computationally efficient and eliminates or mitigates the vanishing gradient problem where you have back propagation and it's approaching zero and it's just optimizing to zero, which is not good. So what it does is it takes negative value and just defaults them to zero. So any negative or zero values will just be zero. Okay. Any positive values will be recorded. And this is, again, an activation or a threshold function that will decide if a neuron, again, so a neuron, one of these circular items actually fires off or the path is engaged toward some sort of insight. Okay. All right. So that's ReLU. And the next argument is going to be input shape. Well, we know the input, so our pictures are 28 by 28 pixels, and they're grayscale. Okay. Sorry, this should be input underscore shape. Okay. So we need to make sure we have 3 parentheses ending, and this is one of those lines that is involved, but we've made sense of all these arguments, and we just want to make sure that the commas are where they need to be and the brackets are where or the parentheses are where they need to be as well. Everything's closed up, so that looks good. Let's save it. Good. Okay, and we can add a comment here. So 32 is the number of filters or kernels that will learn to recognize different patterns in the images. Okay, so kernels are filters again. Let's go back to our lecture here. These are, where do I have that? Okay. These filters will detect things like edges, textures, shadows, things like that. Okay. And this is what a kernel looks like in integer format. This is what the computer will deal with. And so we're deciding on these, what's happening inside these pooling layers here, these convolution layers. Okay, and we've decided on the popular algorithm ReLU. Okay. Okay, so let's save that and keep going. Okay, I just need to make sure I'm still recording. Okay, the next is we're going to create a max pooling layer, and this will reduce the spatial dimensions, height and width, of these feature maps kernels to retain essential features. Okay. So essential features, that's all we need. We don't need anything more. So again, we'll use the model add or the add method, and we'll go layers, max pooling, 2D, capital D, and we'll put 2 by 2. Okay. So here we've reduced the spatial dimensions of these maps. Okay. And effectively, this halves the height and width of the feature maps. Okay, so once it goes through these layers, we are reducing the dimensions, and we're retaining what we just need to focus on in these images, okay? But because it's a neural network, typically the more layers that you add, the better. Okay, not always, but we want to make sure that images are classified correctly. So we're going to add another layer. And so after the max pooling, we're going to add a second convolutional layer. Okay, and because we've already added one up above, we can start to kind of grab the syntax and just throw it down below here. But we're going to axe this input shape, and we're just going to leave in this activation function, the ReLU. Okay, we are, instead of 32 filters, we're going to have 64 in the second convolutional layer, 3 by 3, and then we're going to use the same activation function, and this is going to extract more complex features. Okay, and right after that, we are going to further reduce the dimensions. Okay, so we can copy that up above, and we're going to go further, reduces dimensions. Okay, so another convolutional layer, our second one, and we're still reducing the layers. Again, reducing the height and width of these feature maps. Okay, now we're going to do a third convolutional layer. Once you get these going, it's pretty simple as far as reproducibility. We're just going to grab this in the second one and paste it, and we're going to leave everything the same. And this is essentially a continuation of feature extraction. Okay, so we're doing things over and over again for good measure. Okay. Okay, so we have our pooling layers, our convolution layers, and if we visualize it, these are these here, and we're grabbing these features or these kernels or these filters, and we're doing feature extraction. Okay, that's all we're doing, is we're extracting these features from the images, and then we're going to throw them into the pooling layer. Okay, sorry, into the fully connected layer. But before we do that, actually classifies the images. But before we do that, we need to flatten them. Okay. Okay, we need to flatten them. Why do we do that? So flatten the output to feed into the fully connected layer. So that's our dense layer. And so I want students to keep referencing this. This is where the actual classification takes place. But it's not classifying these whole images. It's just looking at these matrices of numbers, and it's doing edge detection, pattern detection, that sort of thing, from these filters or kernels. Okay, and then eventually we arrive at an output. So how do we flatten this? So we go model add, and we'll go layers, flatten. We call flatten, sorry, that should be capital. That's it. Okay, so let's make sure we have comments here so we understand it. So flattening converts the 2D matrices from the convolutional layers into 1D or one-dimensional vectors for the dense layer, the fully connected layer. Okay, and this is the classification layer. Okay, so again, we're converting to 1D. Okay, whoops, converting to 1D. And we can save. And that's easy. That's just one line here. So you can visualize, you can see how simple it is to actually visualize it, build it out in software, all these layers, these pooling layers, pick the activation functions, flatten the data. We can reduce dimensionality and just focus on the features that we want. And we're now preparing to feed into the connected layer. Okay, and that's this next part. So fully connected layers, it will learn the complex features from the flattened 1D vector. Okay, so we'll go model add. We'll call layers, but this time we're using a method called dense. Okay, and 64. And we call an activation function, which again is ReLU. Okay, and save. Okay, so we're extracting the features. We're using the ReLU activation function, but now we're in the dense layer. Okay, a fully connected layer. All right. Now we are looking at the output layer, so our prediction layer, the Y layer. So this predicts the class probabilities for digits 0 to 9. Okay, so our number system. What does this look like? So again, we use model add. We're going to go layers dense again, but this time we're going to use 10, and we're going to use 10. And if you recall, well, it's 10 filters that we're looking at, and we're going to be looking at a different activation function, and this is called softmax. Okay, so for this, to understand this, we do need to have a look at our activation function lecture. So softmax converts scores to probabilities for each class or label. Okay, so if we go to the lecture, and we should have softmax here. Let's see, we have 10. I think I have softmax. Where are you? There we are. So softmax essentially converts real numbers, vectors of real numbers, into probability distributions. Okay, this is the output layer. So we want real numbers or scores converted to probabilities. Okay, and this will lead to our output. Okay, it exponentiates each element, making them positive, and then normalizes them by dividing the sum of all of these exponentiated values. There's the equation, and there's the output. Okay, so there definitely is some math involved there. Okay, the next part of this, okay, we're about halfway there, so you guys are doing great. Is we are going to compile the model. Okay, compile the model. So get everything together. This sets up the model for training with a specified optimizer. So neural networks will have backpropagation optimizers, which will reduce the loss function. Okay, it'll also give us metrics back that we can track and visualize. Okay, so what does this look like? Well, we're going to access the model again, and we're going to compile, use this compile method. Okay, and we'll go through the arguments here. So the first argument is the actual optimizer argument, and this is going to be set to atom. Okay, so the atom optimizer is a popular one for training these neural networks, I should say. Okay, so we're going to set that to atom. We're going to set a loss argument or parameter to categorical cross entropy. Okay. It's quite a mouthful, but what you need to know is this is a loss function for multi-class classification. So if we're classifying images, we have multiple classes, and this is a loss function for that. Okay, and perhaps we can find out more about that, but we're going to keep going. So we have our optimizer, our loss function, and then finally, we're going to look at metrics. So students have learned certain metrics from the confusion algorithm like accuracy, F1 score, and so on. Here we are looking simply at accuracy. So I believe this would be true positive, true negative over the entire set. So this is what we're going to use for tracking accuracy during training. Okay, so a lot of comments, and the reason for that is we want to understand each line as we go along. Okay, I have a red squiggly line, so I'm going to stop and identify that I've forgotten a comma. Don't forget commas, and if you do see squiggly lines, just make sure they are taken care of. Okay, so save that. And let's keep going. So this sets up the model for training again with a specified optimizer loss function and metrics to track. Okay, so I'm sure there's default, but here we are setting it specifically. Okay, the next part of this is we're going to fit the model using the data generator. Okay, and if you remember, we augmented our data to account for different ranges. So rotation angles, width, heights, zoom range, shear range. And now we have to incorporate that. So what does that look like? We're going to create a variable called history. And we're going to go model fit. Can you use the model fit method? Just like any machine learning algorithm. And we're going to go data gen. But actually, before I do that, let's make another comment here, just to understand it better. So we train the model on the augmented training data that we configured above. And history, this history variable stores training metrics. Okay, why do we want to store the training metrics? Because we're going to use matplotlib to visualize the training metrics. So this is a way to visualize and just to get an intuitive sense for what's going on. So we have data gen, and then we're going to access a flow method. And this takes our training images, our training labels, and we also specify a batch size, 64. So we've been specifying batch sizes in all of our layers here, 64, 60, 32, and so on. And this is no different. So this is using the data augmentation for training. So now we're implementing what we configured up above, and let's put a comma right after that. Okay, the next part of this is number of epoches. So epoches are episodes of training in which we go through the entire data set. So number of times to go through the entire data set. Okay, so we can specify that. And generally, the more epoches, the better. But keep in mind, it does take time. And then finally, we have a validation data variable, and we're going to pass in our test images and test labels, okay, because we want to validate our model. So let's make sure we have that, and we're going to have two closing parentheses there. Okay, so we've called fit before, we've called fit and predict. In a neural network, it works a little bit differently. We specify the batch size here and the epoches, but essentially we're doing the same thing. We're passing in the training and images and training labels, that sort of thing. And here for validation, we have the test images and labels, okay? So same kind of deal, but different way of doing it in a neural network, okay, working with TensorFlow and Keras. Okay, so let's keep going here. Let's keep plugging along. So we're going to create a statement here that evaluates the model on the test set. Okay, what this does is this gives us the final loss and accuracy on unseen data. Okay, so again, we augmented the data because we don't want our model to overfit, where it performs poorly rather on unseen data, and that's why we augmented it. Okay, and now we're setting it up to visualize it. Okay. So we start with test underscore loss and test underscore acc, these two variables. And this is returned by model evaluate. And you can see a common theme here in these Python working in machine learning. We get these sets, typically lists or tuples, that are returned by these methods. And we have this evaluate method that we put in our test sets into, okay? Both the images and labels, and save. That's it. So accuracy and loss, we're going to print with a formatted string or an F string the test accuracy, and we're going to have print squiggly lines, so test underscore acc, and we will cut off some decimal points here. Okay, so go ahead and save that, and this will print the test accuracy. So again, a lot of comments, but we want to be able to understand what's going on here. So as students, if we, well, we should be, but as we build these models in the future, you have an understanding of how these things are mapped out, okay, or built out. Okay, the final portion of this is we are going to plot the data, or the training and validation. And this requires two plots. So we're going to do, and this is why we use matplotlib. So you can see we are nearing the end of this, but it is a little intricate. So we're going to plot training and validation accuracy and loss. Okay, because we want to, again, get that intuitive understanding of what's going on here. So we want to visualize it. So we access the PLT alias from matplotlib, and we're going to create a figure size or dimension, 12 by 5. Okay, so we define the size of the figure. That's our first step. And now we're going to plot training and accuracy. But we're going to use an object. So if you recall, we charted out this history variable, okay, and this is equal to model fit. This will give us the metrics, and we're actually going to plug this into matplotlib in order to visualize it. Okay, so let's start with PLT subplot. Okay, we're going to roll 1, 2, and 1. And this is a subplot for accuracy. Okay, and we'll save that. Okay, and we'll make some more comments here. So history. This object is returned by model fit, which essentially contains information about the training process. Okay, so that's history. And then there's another variable we're going to use in the matplotlib, and that's history. And this is essentially a dictionary that holds lists of metrics recorded during training. Okay, so we actually get this as a return object from this model fit. Okay, and we can visualize it. So let's save that. Okay, so a lot going on here. We don't see history and history yet, but I want to parse those out first before we throw it into the plot. Okay. All right, so now we start plotting it out, and we're going to put in this history. Again, this is a dictionary object, and we are going to plot accuracy. Okay, and we'll give it a label, and this will be train accuracy. Okay, pretty straightforward, and we'll save that. And it's really neat how the model fit will return this so we can visualize it. So let's keep going. Now we're going to return validation. So again, history. Instead of accuracy, we are looking at val accuracy, and these are not defined anywhere. This is just returned as objects from the model fit. And we'll give this a label of validation accuracy. Excuse me. Okay, so we're looking at accuracy and validations accuracy. We'll save that. And we'll give it a title. Model accuracy. Okay. And we'll give it Y and X labels. So Y label is going to be accuracy. And our X label, we've done this before, so this should be pretty simple. EPOSH, so number of episodes. Okay, so accuracy according to number of episodes. And then finally, we're going to create a legend. So far, we've just invoked the legend, but here we're going to use an argument to position it, and we're going to position it to the lower right. Okay, and save that. Okay, so a lot going on. This subplot adds an axes rather. The current figure retrieves an existing axes. Okay. Additional behavior when working with APIs. The subplot will take an index position on a grid with rows and columns. Okay, and it returns the axes of the subplot. Okay, and that's why we have 1, 2, and 1. In the plot, we have this history object with the accuracy and validation accuracy, and then we have our labels. Okay, so something new to students, but the general flow, we've done this before in linear, logistic, regression, and so on. Just a new take. So that's plotting training and accuracy. Now we're going to plot training and validation loss. Okay. So essentially, training is the number of epochs against accuracy for the first plot, and then training epochs and validation loss. Okay, or the loss function essentially. Okay, so we're going to do the same thing essentially. So I'm going to copy this and just paste it, and we're going to change things. So this subplot changes to 1, 2, 2. And we'll change a subplot for loss. And we're going to keep history in history, but this is now going to be loss. And we're going to change this to train loss instead of accuracy, which makes sense. And below that, we're going to get the value loss. And we're going to change this to validation loss. So just some tweaks. Model accuracy changes to model loss, and the Y label changes to loss. We keep epoch, and this position, because we already have lower right occupied, we're going to change this to upper right. Okay. And save. Wow, we've done quite a bit, and we are almost done, people. We have 2 lines left, so let's get started. What are we doing? So we're going to use a method here called tight layout, and we have not used that before. So this adjusts subplots to fit into the figure area. Okay, so we defined our subplots, and it will adjust it to fit inside our figure or a graph, essentially. And then finally, we show it, okay, and save. All right, we are done. So let's start from the top, students, and figure out just exactly what we've done. So we've imported TensorFlow, Keras. We have our MNIST data set, 60,000 training, 10,000 testing images already split and returned from this method. We reshaped to grayscale. We changed to integer and normalized the pixel value. We one hot encoded the labels. So from 0 to 9, this becomes the one hot encoded format. We've augmented the images or the data by accounting for, images that are rotated, zoomed in on, scaled, dimension change, sheared, that sort of thing. We specify in our CNN, our convolutional neural network, that we're going to use sequential layers that we can stack on top of each other. And then we start building out these layers. Our first layer is a convolutional layer. We extract features, 32, 3 by 3. We use the activation function ReLU, and an input shape, 28 by 28 pixels, and this one indicates grayscale. Okay, we have a max pooling layer where we have the dimensions, and our additional layers do the same thing. So we're extracting more features, reducing dimensions, and then we flatten the data from 2D to 1D to get it prepared for the dense layer. We have 64, a batch of 64 here. In our dense layer, or classification layers, we use the softmax function to convert scores, or real number vectors, to probability distributions. We have this model compile, which essentially sets the optimizer, the loss function, and our metrics. And then we define this history as model fit. Inside here, we specify the number of epoches. We pass in our training data and specify the batch size, and also our validation data, which is just our testing data. Okay. We use this evaluate method to return test accuracy, test loss, and we print that out. And finally, we plot out 2 plots. Okay, subplots meaning, half of the screen for each. And instead of just hard coding, we actually used return objects from this history variable, or model fit, to grab accuracy and loss. And we're measuring it against the number of episodes or epoches. Okay, and then we show it, and we're done. So let's play it and let's see if it works. Okay, so train images reshape. Okay, let's see, train images reshape. Of course, in software development, we just need to see. I probably put, okay. So this, instead of underscore for lines 12 and 13, I should have a period. I apologize for that. So let's save that. So just make sure it's train underscore images dot reshape and test underscore images dot reshape. So let's save that. So that looks fixed. Let's try running it. Okay, so we want a terminal open. For this, we get some warnings, and that's normal. And you can see our epoches are running. Okay, there should be 10 of these epoches where it runs through the entire data set. So keep in mind, this is 60,000 training and 10,000 testing images. So this is going to be taking a little bit. You can see during each epoch that accuracy score increases. Okay, and our loss function conversely decreases with each epoch. So this is these are, machine learning model training examples in a nutshell, where we are trying to minimize that loss functions. And if you recall, neural networks use back propagation to adjust the weights and minimize that loss function. We use ReLU as an activation function to mitigate the effects of vanishing gradient. Okay, so this is going to take a little bit as we head into epoch 10, but this is what you get. So make sure students are saving this and submitting this to the Blackboard link. If you have any syntax errors, just go through the video and just make sure everything is what you saw on the screen, and just review the syntax. Okay, but this is training, deep neural networks. It does take time. It does illustrate, hey, that these more sophisticated models that we see out in the world, they can take hours, weeks, days, even months to train, because they, their data sets are absolutely enormous. They deal with big data, huge archives, and a lot of processing requirements. So for us working on our computers, it's not very practical to train very large models like LLMs, for instance, or large language models, just because we need a lot of compute resources. Okay, so we are just waiting on this to finish, and we should see our matplotlib visualization right at the end of this, springing up. So we'll just wait for epoch 10 to finish. Look, you can see our accuracy is at 98%. There is our matplotlib visualization, and it illustrates the time. So the epoch is approaching 10. Our accuracy is increasing, okay? And our loss function is decreasing. But keep in mind, it's not just a straight up line or a straight down line. It does tend to converge here. But you can see our accuracy finished up on 98, almost 99%. So that is pretty good. Okay, so I hope students enjoyed this video code lab dealing with convolutional neural networks. And just make sure you save everything and you submit the file to Blackboard, and we'll see you next time. Thank you very much.